Good afternoon. Welcome to Mastering Math with Tim Sever. In our Introduction to Algebra series, today we're going to be looking at a nonlinear system of equations. Okay, let's take a look at the following nonlinear system. Here you see we have two equations which comprise the system. We're going to try to solve the system simultaneously. And what that means in this case is that we want to find all real solutions to the system. And again, these solutions would be ordered pairs, which are ordered pairs of real numbers. So the first thing that we want to do is notice that the second equation comprising our system, which is x minus y times quantity x squared minus y squared equal 24, we want to observe that the x squared minus y squared term can be factored as the difference of two squares. And you can see that I'm factoring that now. We get a new system where the second equation is replaced, where that term has been factored, and then we simplify, getting x minus y quantity squared times x plus y equal 24. Now, what this allows us to do in our system is to try to solve simultaneously. Now, usually when we try to solve simultaneously, we try to eliminate a certain variable or variables. Now here, since they're nonlinear, that may be a little difficult. So what we're going to do is do something a little bit out of the ordinary, and we're going to divide. Well, actually, we're not going to divide. Let me rephrase it. We're going to look at the quotient. Let's look at the top equation. So if x plus y times quantity x squared plus y squared is 120, and if our second equation of the system, which is x minus y quantity squared times x plus y is 24, if those two things are true, then that quotient has to be 120 divided by 24, which is equal to 5. Now notice I'm writing 5 as 5 over 1, but first, the primary reason for forming that quotient, as you'll see, is that we can cancel the x plus y terms. And we'll speak to, later at the end, I'll make a comment as to why x plus y is non-zero, and why we can then, those terms will divide out as I'm showing you here, so that we can multiply both sides by the common denominator, least common denominator. Some students call that cross multiply. I'm not a fan of that terminology, but if you've heard that terminology before, you're starting to think of that term in terms of what we're doing. What that will do is it will remove the fraction from the problem, and then we will get an equation that doesn't have any variables in the denominators. All right, once we do that, we get the resulting equation. X squared plus y squared is 5 times quantity x minus y squared. As you see here, we want to multiply out the right-hand side, which is a perfect square trinomial. And I'm not showing the step here on the screen. You can distribute the 5 through the trinomial on the right-hand side. Then, as you would expect, we want to write the quadratic trinomial in x and y in standard form. Namely, we want to get 0 on one side. And then when we do that, you can see here that we have a common factor of 2. We need to factor on the left-hand side and then divide both sides by 2. This will yield the equation 2x squared minus 5xy plus 2y squared is 0. And it turns out this is quadratic in x or it's quadratic in y, either one, whichever suits your fancy. But turns out this is factorable. This is reducible. So you can see I'm factoring it here, and we obtain 2x squared minus 5xy plus 2y squared is, in fact, 2x minus y times x minus 2y. And of course that product is 0. This allows us to solve for each linear factor, producing ultimately y is equal to 2x or x is equal to 2y. Okay, now remember we're solving simultaneously, so now we have to do these branches, so to speak, one at a time. We have to consider y equal 2x, then later separately we'll consider x equal 2y, and we need to plug that result back into either of the two original equations. I'm going to choose the top equation, as you can see here. Substitute 2x for y in one of the equations comprising our system. I will use the first one. This will give me, as we simplify, 2x squared is 2x quantity squared is 4x squared, and when we add like terms and multiply, we will get 15x cubed is 120. Solving, the first thing we want to do is divide both sides by 15, and 120 divided by 15 is 8. And now we have a simple cubic equation to solve, x cubed equal 8, and we will take the cube root of both sides to yield x equal 2. Now remember, there are two complex solutions which we're not interested in. Remember, the point of solving here is to find the real valued solutions to the equation. So we get x equal 2, but since y was equal to 2x, we need to plug in, and for that value of 2, we get a y value of 4. So this tells us the ordered pair 2, 4 is a solution to the system. That's great. We found one solution. Well, technically, we don't know that it's a solution yet. We really should check that via direct substitution. That exercise will be left to the reader, but it is in fact a solution. You can verify that yourself directly. Now, using the other branch, x is equal to 2y. Again, I'll plug that into the original system, and that will give us something very similar. There's an aspect of symmetry to this system which we could discuss later. We get 15y cubed is 120, very similar to the first equation. And again, dividing both sides by 15 yields y cubed is 8. Again, for simplicity, taking the cube root of both sides yields y is equal to 2 is the only real solution to that equation. Now again, we have to plug back into our line x equal 2y for that value of y equal 2 to determine that x is 4, which will produce the second solution, 4, 2. Again, strictly speaking, from the standpoint of logic, those two proposed solutions, let's say it another way. Strictly speaking, from a logical perspective, we know at this time if there are any solutions to this system, then there are only two possibilities, 2, 4 and 4, 2 as ordered pairs. We need to check those via direct substitution to verify whether any of those ordered pairs are in fact solutions, and they both are. And this leaves us with the final conclusion that the only two solutions are, in fact, those two ordered pairs, 2, 4 and 4, 2. Now, here's the comment that I was going to make. When we form that quotient, and you could do that, you could say take the original equation and divide both sides by x minus y squared times x plus y. You could easily do that and then get the same problem that we had to start with. But the question, remember, you don't want to divide by 0. So really, when you form that quotient, or you think of it as a mathematical operation of dividing both sides of the original equation by that term, you need to be certain that that denominator can't be 0. Technically, the term that you really want to divide by, which will be in the denominator, can't be 0. And of course it can't. If that whole term was 0, then either x minus y is 0 or x plus y is 0. And in either case, if either of those two terms were 0, then their product could not be the number 24. Remember, 0 times anything is 0. So by virtue of that product, x minus y quantity squared times x plus y being 24, we know for a fact that neither of those terms can be 0, and in forming that quotient, we're on absolutely solid mathematical grounds. All right, I hope you enjoyed this problem, which was non-traditional in its nature. So it's nice to sometimes look at the graphs of these equations to see what's happening. Although this video is primarily intended to be analytical in nature in terms of how do we do the mathematics. But let's just look at the graph so they can verify what we have done analytically, and to also show how these curves look in two-dimensional space. So here you see the graphs. I've used graphing software to graph it. The red graph is our top or first equation. The blue graph, which is discontinuous, it's not connected. You see that in two different pieces or branches. The blue graph is the bottom equation, the one that we factored and we dealt with secondarily. And you can see I've overlaid the 2 points of intersection, 2, 4 and 4, 2. And you can see those are in fact the only 2 points of intersection. And if you look at it, you can also see there's an aspect of symmetry there, which I'll discuss now. So if you had the line y equal x, which I'm superimposing onto this picture, you can see that if the graph were folded about that line y equal x, then the one piece would land on top of the other, or you could say it's invariant under that transformation, which means it's symmetric in that aspect. Now, in terms of the equations, what that means, if you switch the places of y and x, if x were y and y were x in both of the equations in our system, you'd have the same system and you'd have the same graph, same points. That's why you see the inherent symmetry in our solutions in 2, 4, and if you reverse those two, 4, 2. Next, let me show you, just for fun, let me overlay those 2 lines that we found, y equal 2x and x equal 2y. They're purple and black respectively. Y equal 2x is purple, x equal 2y is the black line. We could also think of that x equal 2y as y equal 1/2 x, with just a lower slope. But nonetheless, you can see that they intersect both graphs and intersect each of the graphs at exactly 1 point. Y equal 2x intersects at 2, 4. That's in fact how we found the point 2, 4. If you go back and look at the notes, look at the video, and if you look at x equal 2y, it intersects the graph at exactly 4, 2. So I hope this graphical exploration helps you kind of get a feel for this problem. And there are other aspects you can see. We can clearly see some asymptotic lines there. Looks like y equal minus x is an asymptote. But in any event, thank you very much, and we'll see you on our next video.